Good afternoon. I'm Denny Erickson. I'm a member of the 60th Anniversary Task Force, and I want to tell you that once in a while, you get to plan an exercise or an event that is characterized by pure joy, and I think we're going to have one this afternoon. This is a very special afternoon. It's going to involve a very special person, and I think we're going to see some very special things from this person. I want to take care of some hospitality things first. We have a number of visitors in the audience. In the event we have to evacuate the auditorium, I'm going to ask my laboratory colleagues to make sure that our visitors are well taken care of. But generally, for our visitors, you want to go back out the way you came in, that way. So as you leave here, take a left through the back door. As you leave through the side door, take a right and then outside. And then for laboratory veterans, you may go either way. There are restrooms, and I know I'm going to get this wrong, but I'll practice for tomorrow. I think the women's restroom is off here to the right, and there'll be a guard that will help you find the right door. There's a men's restroom off to the left, my left, and again, there's a guard position that will provide some help. With that, let's begin the afternoon. I want to introduce Alan Bishop, the division leader for our theoretical division. T division is one of the several divisions left that goes back to the historic foundings of the laboratory in the Manhattan days. With that, Alan is the master of ceremonies for this afternoon. Thank you, Alan.
Well, it's wonderful to see such a large audience, and although this is just one in the rolling celebration of events that Denny and his committee have organized for us over the next several months, this is a kind of special oasis for me personally, for T Division, to be able to honor Frank Harlow with today's events. There are really two events. One is that Frank is approaching, not quite there yet, but approaching his 50-year anniversary with the laboratory. The second is that he will be giving the inaugural Heritage Lecture on a lifetime, in fact, I would say Frank's lifetime, in turbulence. And these two events together encapsulate the extraordinary career of an extraordinary individual, a scientific leader in the grandest Los Alamos tradition, a builder of technical teams and groups at the laboratory, whose expertise has been and remains fundamental to our missions, a teacher and a mentor and motivator of many generations of students, young and old, and an artist, as many of you will know, of wonderful creativity. And not least, as a treasured friend and colleague to a multitude of past and present Los Alamos alumni. So Director Nanos has kindly agreed to make the presentation of the 50th anniversary to Frank, and then John Hopkins is going to introduce the inaugural lectures. And I remind you not to leave, because when the events here are concluded, you are all invited to a reception for Frank in the study center. So.
Thank you. Well, Frank, this morning I made a crack at the all hands about the fact that we were having difficulty getting people together for technical discussion and talks. And I want to thank you for solving that problem for Los Alamos this afternoon. Would you please come up and join me on stage, please? You have had an absolutely remarkable career, 50 years here at the laboratory, starting coming from the University of Washington in September of 1953, and spending a full time engaged in theoretical research, and just not in any area, and probably, I think, theoretically one of the hardest areas that there is to tackle, most of us knew better than to get involved in turbulence. No, actually, that's only a crack. It's just a very, very difficult and demanding set of studies, and yet one that's so critical to almost everything in the physical world. I'd like to present you with this certificate signed by President Atkinson, myself, and Alan Bishop. With appreciation and gratitude, the University of California, the Los Alamos National Laboratory, and the laboratory's theoretical division congratulate and recognize Francis H. Harlow on 50 years of extraordinary service as a member of the laboratory staff, as an employee of the university. Your 5 decades at the laboratory are unique and historically significant, and a remarkable career spent entirely in the laboratory's storied theoretical division. You have maintained an uninterrupted focus on the theory and modeling of turbulence. Accomplished scientist, valued colleague, and esteemed mentor, you have contributed brilliantly to your field and to Lionel's mission. We salute you for your outstanding contributions to the laboratory, the university, and the nation. Signed, Richard C. Atkinson, President, University of California, myself, and Alan.
Thank you very, very much. I appreciate the wonderful words. I feel tremendously honored by your presence here and by this certificate. I didn't even think about how I should practice giving a talk here, so I'll just simply say again, many, many thanks. Okay, you want to?
Very good. So, John, you're going to take over now?
Yes.
Thank you.
About 6 months ago, Roger Mead and I suggested to John Brown that the laboratory initiate a lecture series that we called the Heritage Series on historical topics that shaped our laboratory and culture. We visualized 3 or 4 all-lab colloquia a year with interesting speakers discussing some facet of our history. For example, possible speakers could include Harold Agnew, Herb York, the first director of Livermore, and Dick Ashworth, a retired Navy 3-star who was the liaison between the laboratory and the military during World War II and the weaponeer on the Nagasaki strike. The list goes on, but we're losing more of the old-timers every year. John Brown endorsed the idea, and Denny Erickson suggested that the inaugural lecture be incorporated into the 60th anniversary celebration. This afternoon, we'll kick off the first lecture of the new Heritage Series with a talk by Frank Harlow. Even though Frank and I have been friends for over 40 years, I'm repeatedly surprised by the diversity of his interests. First of all, of course, Frank is a world-class physicist with a 1953 PhD in quantum field theory from the University of Washington in Seattle. You'll hear more about Frank's scientific pursuits in his lecture. Probably most of you know that he is a professional level expert on Pueblo Indian ceramics with many books and articles to his credit. Perhaps fewer of you know that he is also an expert on brachiopods and has written technical papers in that field. He is a cello player and in the distant past played with the Seattle Philharmonic. He is an accomplished artist and painter. His works are in museums, in private collections, and here in the laboratory. Perhaps you also know that Frank is a motorcycle buff. I find it particularly amusing that Frank's former pride and joy, a 1940 Harley, just a slip there. is in the New Mexico Fine Arts Museum as an example of a mid-20th century multimedia sculpture. Frank and Pat, his wife of 51 years, have 4 grown children and reside here in Los Alamos. Please welcome Frank Harlow, who will talk to us today on 50 years of research at Los Alamos, a lifetime of turbulence.
Thank you, John. Appreciate that very much. And thanks to all of you who've come here. This is a real special occasion for me. So what is this thing that we call turbulence? It's kind of funny about this. It's an extremely difficult thing to define in some real rigorous fashion. What is turbulence? Well, we all know it when we see it. For example, if you have a fire that is burning, flames licking up this way, that, you say, hey, that's turbulent. And same with wind, if it's whipping back and forth on your car as you're driving to Albuquerque, or in an airplane that says, hey, this is going to be turbulent up here, you know perfectly well what that means. Boiling water. There are lots of circumstances in which you know what turbulence is. It really means a fluctuating facet of flow that is small in scale compared to the overall dimensions of something you're talking about. And it's the something you're talking about that makes it hard to define. But if I have a fire this big and flames this big, then I call it turbulent. If I have a fire this big and a flame that same size as from a candle, okay, then I say, oh, that doesn't look turbulent at all. But from a practical problem-solving point of view, turbulence is really the fluctuating part of a fluid flow that we cannot easily resolve by computer calculations. And the word easily is important here because I will be showing you some calculations that, in which you do resolve the turbulence. But it's hard. It's not an easy thing to do. And we'll talk about that more in a bit. So why are we interested? Well, for a lot of reasons. One of them, of course, is the national defense programs. In the earliest days, the response to the idea that the Germans might be making some kind of a very strange, large, powerful weapon, and let's get together, at the suggestion of Albert Einstein, let's get together and see if we can figure out what might be going on and what we could learn about the process. Well, almost immediately, one of the main problems that people realized is that you could have a lot of turbulence occurring in a circumstance of a nuclear explosion. Well, there are other things like stockpile stewardship and, in general, predictability and follow-through. Well, follow-through, by that I mean we started to understand back in those days the importance of turbulence for our particular kinds of things. Turbulence was known, of course, for a long time. And we feel as though we can't stop now. We've got to understand what it is that we opened up as a major point of concern, a technical issue that needs to be solved. And it's not an easy thing. As a matter of fact, one of the delights of it all is the idea of a challenge. What is it, a red flag in front of a bull or something like that? Anyway, Nobel laureate Richard Feynman sort of issued this challenge when he said, hey, look, describing turbulence behavior is the hardest unsolved problem in classical physics. Now, you have to say classical physics because there are lots of even harder problems in modern day physics. Here's a kind of a fascinating picture. This was taken from a set of badge photos that covered the main number of people in the laboratory, from which we've picked out some of the people from T division. And amongst them, we have on the upper left here, Richard Feynman, who made the challenge there about turbulence. We have people like Hans Bethe, John von Neumann, and Nicholas Metropolis, very, very famous people who went on to win Nobel Prizes, who were just the founding people of the work that this laboratory went on to do. All of them very famous, but for the fellow that I put down there on the lower right, Klaus Fuchs, who was perhaps more infamous than famous. Well, that's enough talk for a moment. Let's take a look at what turbulence really is. And there's nothing in my mind that is more dramatic than to look at the behavior of Mount St. Helens during its eruption. The first picture here shows just a still of the crater and the nature of the smoke that is coming out there, the volcanic ash. You see one of the things here that is of particularly interest to us. Large scales. Oh, can we dim the lights a little? That's a good idea, thanks. What do you do, dim the... I think they'll work on that. But for the moment, let me just simply say, thank you. Let me just simply say that one of the tremendous and intriguing challenges associated with understanding turbulence is associated with the idea that you have intermingled scales, large scales, tremendous big blobs like this, okay, and smaller scales like these little things right here, and tiny little scales like just the little bit of puffs that you see there, and they all overlap with one another. Well, what if you look at this thing now from the standpoint of how it evolves? Let's take a look at a movie that will show us now a little bit of the lip of the crater and some region just about here, and watch as it comes roaring out in a very turbulent fashion. There. See the lip of the crater? Look at that. One of the things I like about this film is the big heavy rocks that are falling down, especially on the right-hand side. The reason that that's fascinating to me is because if you go out to the end of Los Alamos Mesa and look at the volcanic ash out there, you will see chunks of much darker material that have been, all around the softer ash has eroded. And here are these large chunks that are present there that flew out from our crater back here and just landed in clumps out, and can be seen out there by anybody who cares to stop by and look. If you want to know exactly where, it's just beyond the industrial park on the right-hand side, and I can show you in more detail if you want. But this one now really made the, the business of a lot of rocks coming out. And at the same time, you see these huge, big eddies, intermediate scales, smaller scales, all going together in a very impressive fashion. There's another kind of thing that you can see out in the field. One of the things that is of particular concern to us is wildfires. And Warren Young was able to get for us some very nice footage of the dome fire that occurred south or southwest of Los Alamos some years ago. There, thank you. Now, this looks very slow. In fact, you look at this, you say, oh, you've just got a still picture. But as we get closer to it, we'll come in on it. Well, you can see some motion over in here, okay? But it's a very slow thing, but we'll focus in now. You can begin to see this roiling set of things that are very much like what you saw at Mount St. Helens. And here most especially right up there, okay? And you saw at the last an airplane flying by. Okay. Now, can such a thing be calculated? Can these things really be meaningfully calculated. Not artist renditions that come from, let's say, one's imagination, that make all these wonderful sort of commercials that you see on television. 3? Keep it going. Yeah. So what we will see is actually a series of calculations that resolve the turbulence. I mentioned that if you put your mind to it, you can actually resolve a lot of the details of the turbulence. Sometimes you have to model it, and that's another story that's perhaps more the story of my lifetime, is how to model this turbulence. But the direct calculations are shown by some things that Rod Lynn and John Reisner did to calculate the dome fire and a fire near Los Angeles and a pollution dispersal fire. Okay. Here we have now a fire that gets started right there. Look at the calculation of all those bumps. Now, this takes place, the calculation is presented much more rapidly than would really occur, much more rapidly than real time. And it's amazing to see how the calculation can calculate represent the transport of the flames and the great roiling set of things up above. We'll see that through a second time now. I think that's a really fascinating depiction of a very complex process. Now here is a much more impressive thing even than that. Right down here is a little bit of a start of a fire. This is the Calabasas or Coral Canyon fire that occurred in, well, I don't recall when. I think I have a note to that. Yes, 1996, and it hurt people. People up there on that point right there were hurt because when it started down here, they thought they had about 2 hours to slowly move back. Well, it occurred in 20 minutes. And the calculation shows the same thing, that in about 20 minutes, the thing had gotten up to that point and was going along. This is now the burned out region. This is the flame approaching up here. The people from the Los Angeles Fire Department have been absolutely just tremendously impressed with the kinds of things that can be done. And we've been interacting with them quite a bit and trying to do something that is going to be a real, meaningful thing for some of their design circumstances. Now this calculation here shows the propagation of hydrochloric acid fumes from a hypothetical excuse me, from a hypothetical accident at Cape Kennedy. The NASA asked us to show this, to do these calculations in order to see how this pollution, how this dangerous stuff is, these fumes are going to get across in the vicinity of people who might be there. So we did that under a NASA contract that worked out very well. Now, what about bringing turbulence down to the scale of the laboratory? I've shown you things that are large-scale turbulence. What about coming down to the scale of the laboratory? Well, my friend Malcolm Andrews and his students at Texas A&M University have done a fabulous job with a 2-level water tank in which you have water in a long tank. The tank is, I don't know, actually a little longer than this and about yay high. And it has a splitter plate right here with water coming in at the top and water coming in at the bottom. And the way they get this instability to go is either by making 2 different velocities of input so they shear against one another, or to make the top one cold water and the bottom one hot water. And it's this latter that we will see in the following movie. Well, let me just say, here, the splitter plate is up here, and it comes in through here, And here's how the two fluids mix together. They mix with all these strange sort of fingers, some of which have these sort of mushroom caps or umbrella caps. We'll be watching as the camera is fixed place and the flow is going past. Let's see. This should be a VHS movie. Well, this is a. Oh, here we are. Okay. See, it's flowing past, and this is actually the experiment. The thing is lit by a laser sheet, and the cold water is coming down. Those are the light-colored fingers that were dyed with a fluorescein dye and lit by a laser sheet, and the hot water is down below. Now, the question is, can we calculate that? And the calculation of that process is something that is really a beautiful piece of work that was done by Tim Clark using his lattice-Boltzmann code. And we shall see now as if we were following along instead of watching the thing go by. As a matter of fact, if you look now at this slide, you will see that here are three different calculations. This one, and this one. They're all essentially the same in overall, high density above low density, things of that configuration like that. But they start now with very different, slight wavelets across the surface. They're all three of them are different from each other. And the question is, what about the overall properties of how these things mix together? The width of the mixing layer, the average density across the mixing layer. How well does that work out? Well, let's take a look at how these right here were generated. Here we see now, at the initial condition, you can hardly see the perturbations. Aha, look at that. Coming down, see the mushroom type clouds there, that form there and here and down here. Okay, these are the things that are contributing to the overall rate of coming through. Notice that you start off with very fine scale, but ultimately the scale. The mean scale of the whole thing just grows and grows. Gets bigger and bigger as these things keep coming together. And pretty soon now you have only about 5 main fingers going across the whole thing. Now this is kind of a dark and muddy slide, but I wanted to show it to you because it is a real historical triumph. It showed us something that we had postulated would occur in the vicinity of a turbulence layer. That is to say, the propagation of bigger and bigger and bigger pressure pulses out. And we worked to figure out how to represent that mathematically in our calculations. And Tim took his results and plotted these pressure contours, which up close are just little things. Then you see them twice as big and sort of 4 times as big and bigger as you get further and further out. And we now believe that it is those larger and larger scales that gradually drive these bigger and bigger fingers of interpenetration. Well, what are the ultimate results of turbulence? Quiescence, shear. You take quiescence and heat. You take a bucket of water, stir it all up, and the ultimate result is that the whole thing just finally dies down, very quiet. Maybe all that's left is sort of an overall big scale sloshing, but it has died down. and it's gone to heat. Now, what do I mean by going to heat? Well, the business of heat and mechanical energy is something that was investigated a lot of years ago. And let me just describe it this way. If I take my two hands and rub them together very fast, by golly, it doesn't take very long before they warm up. Same is true if I take a fluid and stir it very fast. My mechanical energy will go into heat. Now, there are other things. Dispersal, turbulence does dispersal. Order becomes disorder. And I knew that I just had to throw in one technical facet to all this. The entropy has increased. Well, here's a sort of a homely example of what I mean by going from order to its disorder. If I take a nice brand new automobile, oh man, off the floor, and it's all polished and shiny and all, and I drive it for some number of years, and it begins to, this and that, and finally it gets to the place where I'm not so sure that it's going to be safe for me. And so I figure, well, I can send it off down to the local wrecking place, or we could put it out in a field, maybe to make some kind of a boundary for an arroyo or something like that. And so you put it out there. Oh, it's been done. I don't know. And the thing sits there, and it rusts, and the upholstery decays, and the whole thing kind of falls down to the ground. It gets more and more into little pieces and rust flakes and all that stuff. And pretty soon it rains, and they wash down the gully, and the wind blows, and they go this way and that. And that is now a state of complete disorder in the sense that I'm talking about. That is the final way that the turbulence has done its job. Many of you are aware of the work that Kathy and Bob have been doing out in DX Division with their gas curtain experiments. And there's a beautiful example of exactly why it's such a useful thing to do that comes in particular from the interaction of a shock wave with a cylinder of gas. Now, how on earth could we do such a thing? I would never be able to think up something like that, but they figured out that if you could make a shock going from left to right by starting off with this being high pressure right here, this being fairly low pressure, the shock would come across and hit this thing right here. Well, what is that thing? You have a little hole in the top of your tank, little hole in the bottom, and very gently you pour in a stream of sulfur hexafluoride, which is a very, very heavy gas. And it goes down in a nice, smooth fashion and gets sucked out the bottom. And they can look at this by putting a laser sheet across this such that you can see what happens. Well, in the next thing, you'll see a couple of things that in this view graph that was furnished to me, but concentrate now on this. Here is now looking at this initial round cylinder of sulfur hexafluoride. The shock has come by, and it gets deformed, and more and more. And look what's happening around the edge. All kinds of little fluctuations. And that's turbulence because it's smaller than the whole overall thing. And so we can call that actually turbulence. Now, Cindy Zoldi has calculated the behavior here. And you see how indeed the very sort of thing that we saw in the actual experiment is formed here as a result of the shock going across the cylinder. Well, there are a lot of examples of turbulence, and I don't want to really, there's as many as you could possibly think of. you know, like pan of water. Actually, a pan of water on the stove, you say, well, when it starts boiling, it's turbulent. But long before it actually starts boiling, you have these little fingers of motion that go on in there that you could see if you put a very fine powder in there. But one of the ones I wanted to also show you is not only can we bring things from the dome fire level down to this laboratory, but we can go the other way out into outer space. And Steve Hench gave me a few beautiful pictures. This is what's called the Eskimo Planetary Nebula. It is got these powerful gases. This is like a big bubble that's being blown out. Out here are all these clumps with tails on them, like comets. And when the thing broke up into pieces, it did so because it was unstable and it was tending to become very turbulent. And I think this is a wonderful thing. The Hubble telescope has been an extremely powerful device for seeing these kinds of things. Here's the famous Crab Nebula. It was a supernova that is an exploding star, a star that was about 10 times the mass of our sun, that started, and it occurred, appropriately enough, on the 4th of July in the year 1054. And it was such a powerful explosion that actually it was observable. The Chinese in particular made records of it. For several weeks it was visible in broad daylight. But you can see that when it exploded, it was like Mount St. Helens. All these roiling masses of material went flying out, and you have all kinds of different scales from the very largest scales down to intermediate scales, down to very fine scales. Outer space behaves just like inner space. Other examples of turbulence include the business of dragging. This is probably the most important thing of all from the standpoint of, well, not necessarily. I mean, it's very important from the standpoint of what you're going to get as effects of turbulence. If you have a submarine going through the water, if you have a truck going along the highway, or an airplane going across through the sky, a lot of the gasoline that you buy to fuel that thing is going into just simply pushing yourself through the material, whether it be water or air or whatever else. You have to contend with the fact that around the edges of this thing, it becomes very turbulent. And turbulence just simply sucks away the momentum of this particular vehicle. Material mix, okay, the orange juice, cream and coffee, fuel and air in an internal combustion machine, and the old admonition that you get from the pharmacist, shake well before using, because they want you to make some turbulence that will mix up the materials there. Well, here's a very homely example. A bucket of still water, and you take a handful of fine sand and very gently put it in there, okay, without stirring it up, and it comes down more or less as a nice orderly sort of motion. But if you stir it all up to start with, and then put your handful of sand in, it just gets dispersed all over the place and mixes really thoroughly. Well, I'm sure you're all going to rush home and do that experiment just because it doesn't seem. All right, let's look at another wonderful example of an internal combustion engine. This is something that our group has been particularly concerned about for many years, is how to make internal combustion engines more efficient, more fuel efficient, less noxious emissions. And we have some wonderful calculations that show you how the turbulence affects this. First of all, this is the one I'll show you an example of. It's a, what do you call it, an opposed piston engine, where you push this way and this way both. And it's a real challenge to figure out what's happening. Well, the way they do it is they have this combustion chamber, and they set off a spark into the fuel, and it pushes it out very rapidly. The upper part comes to these exhaust ports, and the lower part comes to these intake ports. And when you get this, when you see in the movie, it gets to the intake port, you will see this great swirling vortex of turbulence that brings in the new, fresh material. Now, there we go. I should have practiced the sound effects more. See, it comes down here, and right from the sides, you see this great swirling vortices that carry the fuel in and the material in, swirls it around, mixes it, and you hope to get great efficiency by having it mix well, but not carry the heat too badly towards the side. We'll see it from the side, and then we'll see it now from the top. You can see even before, there it comes in from the lower ports, and swirls around. We'll see this again. I mean, there's turbulence here now to start with, okay, but it especially becomes noticeable there when the stuff comes in from the side. This second one was a little bit slower than the first one, okay? And then the third one is fast again. This work has become very famous. The Kiva code has gone all over the world and is used by all kinds of wonderful places that are putting it to use both in this country and elsewhere. Well, along with the business of looking at what happens to the fuel when you burn it, also how do you take crude oil and make it into some or another kind of products like gasoline and the Vaseline you put on your lips or whatever. Well, the way that we are going to see this is, first of all, an experimental film that came from the Amoco Oil Company. It's a very nice example of the kinds of experiments you can do. The catalytic converters are, yay big, so I don't know, huge things around, many, meters high. But the model that they made is about, I think it's about this big around. They cut it down the middle so you can see what happens in the interior, and it roils and boils. There's the device, this sort of central core. You can already see that it's the surface up here is starting to go all over the place. Some streams are coming up near the wall. And when we look up here, we can see lots and lots of sloshing turbulence. How would you ever calculate a thing like that? How would you ever design one of these catalytic converters to increase its efficiency? Well, this is a big challenge. This is something that we've done quite a bit. Here they are, I can't look too much. I'll fall right off the... Now, the calculation of this is something that's really quite an interesting thing to see. As you can see, if you cut it in half, you can see where those things are going up those fingers of turbulence. You can see how it's squirted in down below and goes up through there. And that goes a long ways to helping you towards understanding what you can calculate with an appropriate set of good equations. Well, I've talked about all these scientific things, okay? I look out here, and what do I see? I'm really delighted I see a big crowd of people. Well, can a crowd of people be turbulent? I'm not going to go into this a lot, but we've actually examined that question with some computer studies, some mathematics, that uses a lot of the same equations that we use for our turbulence in water. You see the people all swirling around. Warren and I didn't really quite know for sure. We think this was in India. but we're not positive. It's a very short, brief thing, swirling back and forth this way. I think those guys' names were all Eddie. Well, we want to calculate turbulence. I've mentioned this over and over again, and there are two main ways to go about this. One is with the direct numerical simulations that you've seen here. The other is what we call averaging techniques to capture the essence without resolving the details. We want to apply this to a lot of our calculations where we need answers coming out pretty fast. We don't want to go to all the expense and trouble of running things. So we developed what are called turbulence transport models. And I'm not going to show you much about the turbulence transport models, although that has been a principal focus of my career, is to develop these things and see if we can make them really work. Here's a funny little homely example about the business of details versus the overall picture of something. I don't like it when speakers cover up parts of the view graph, but I finally decided that was a good thing to do. I need to become humbled by the things that one needs to do. Okay, all right, look up here. See all those dots? They're clearly in some or another kind of pattern. You look at that and you think, I wonder what that could be. Is that a bridge going across a river? Is it whatever? Okay. Well, let's step back a little bit further. And we see now something is beginning to emerge. And some of you will actually be able to look and say, I think I know what that is. But let's verify whether or not that's true by looking at this one. And what we're seeing, you see, is this right here. Now, I don't want to look through the newspaper and look at all the dots in every photograph. I want to get the picture of what's going on, the essence of what the particular picture is showing us. And that's what we do a lot all over what we're doing in materials, in turbulence. As a matter of fact, here's some pictures of some of the details that we need to represent. And we don't want to calculate every single last part of it because we would be calculating forever. Here's a beautiful example that Jack Hills let me borrow. That's my fingers there. This is a meteorite from the Namibian desert of South Africa that fell who knows when, but it was brought in and it was cut in half. The outside part of it is just kind of brown and a little bit rough, but the polishing here shows a really, really complex, fascinating crystal structure. This is iron nickel material, an octahedrite pattern it's called, and it's a very beautiful example of something that if you had to calculate every detail of that piece of metal, you'd never get anywhere. You need to have what we call homogenization techniques that take all the details and put them into some kind of a model for what's going on, and it has to be meaningful. Here's another one I think is really pretty. This is now an experiment that was done by Ben Henry, and Tom Mason was the one who gave me the picture. This is now a tantalum plate impacting a piece of tantalum. And you can see up here the complex structure of the crystal grains. Virtually every metal in nature is made up of little grains, little crystals, actually, of the particular metal. And these are shown in terms of, different colors mean different orientations. The important and meaningful thing, however, is not what's happening to all these little grains, but what's happening to the overall plate, or plates. There's a big fracture that's going clear across the whole thing. It's breaking apart. That's what you would like to be able to predict with your code. It's whether or not it will come apart, how it will move when it comes apart, things of that sort. Here's another one that combines the metals with turbulence. This is now something that Paul Cooper furnished me from Sandia. It's something called explosive welding. Now, explosive welding means the following thing. If I have two sheets of metal like this, one of them, in this particular case, one of them is nickel and one of them is steel, and I put explosive a slab of explosive on the outside of each one, and I detonate it down here, and the detonation goes burning up this way. The plates come together like this, and actually some slippage, so that there's normal impact forces, and there's slippage forces. And at first, it flows what we call plastically, and it flows relatively gently, but then it sort of freezes, just like that. And it freezes into this kind of a pattern, which you see when you cut it across. And here now is the interface between the two, with these things locked together like this, and really very effectively explosively welded. I'd like to go way back to the beginning. And I do this just because it was such, you can hardly believe how exciting things were here in the laboratory. I was lucky to come in the 50s. By the latter part of the 50s and the early 60s, we were doing things that were crude and very unsophisticated, very simple numerical techniques that nevertheless were giving things that just knocked our socks off, and that really, I mean, this doesn't sound very modest, but really they were influencing the whole technological world by showing the kinds of things that could be done with a computer, that it was meaningful, that it was realistic, crude as it was. Anyway, these are the people right here who were the staff at that time, just a small group. People, we've got 4 of us are here today, Tony Amson, Dan Butler, Bart Daly, and myself. The others we keep in touch with. I think there's only one that I'm not exactly sure where he is right now, but they were a fabulous group of people. You know, just, I can't say enough. Here's an example of a calculation done in the 1950s with a thing we call the PIC method, the particle and cell method, where the fluid is represented by a bunch of discrete particles. One of the things that was very troublesome to the early days people who were trying to do calculations is if you have 2 different materials that are going to crinkle amongst each other, how do you do this in such a way that it gives you good answers? Well, we put particles into cells and followed using the equations of fluid dynamics, the physics equations, and we got this. Now, one of the fascinating questions to us was, is that turbulence? You know, is it? We saw the calculations of air onto neon, the interface there is nice and smooth. Air onto carbon dioxide, the interface is nice and smooth. But air under helium, where there's a big density difference, began to get all crinkled up, very much like the things that were done much more carefully by Tim Clark in later days that I showed you earlier. Well, we didn't know how to answer the question at that time. We did calculations of a variety of sorts. This is a sluice gate that is opening up right here at t equals 0. This opens up, and the water comes pouring out like this. Here again, you ask the question, is this really turbulence? Well, in a way, it didn't matter. This went on the front cover, I believe it was of Science magazine. This was articles. It was translated into Japanese, Russian. It was, crude as it is. It was something really special. It's like I don't know, the first Edison light bulb or something like that. You know, it looks real crude now, but it was very special to us. Here we see now that we were actually getting comparisons between calculations and experiments. It's backwards from where it was in the other picture, but here's the water coming down in the sluice gate. It kind of jiggly, a little jumpy, all that stuff. It hits the wall over there about the same time. The return wave now is heading back in both cases. Here's the return wave, comes over and hits. Now, it hits experimentally a little sooner than it hit calculationally. Oh, well, we weren't perfect. Probably we still aren't, but on the other hand, it was very special. The experiment is kind of simple, but it's really cute, and it's a very effective way to compare things. That's what we always need is experiments, good experiments. And we get them from different parts of the laboratory, and it's very wonderful. And from other parts of the world, it's very wonderful to have experimental data that you can compare your calculations with. Now, what is this? This is the first time that we actually got something that really was a fine calculational result to be compared with experiments. What I'm talking about now, this Kármán vortex street, all of you be real quiet now, okay? See if you can hear what I'm going to produce. You hear the tone? I don't know if you could hear it in the back of the room. That is what we call Kármán vortex street. The air going past the rod, or the rod going through the air, is very unstable. And on the downwind side of this, it gets very messed up, it goes very turbulent, makes a sound that you can hear, and there's a very definite frequency that is associated with it. And so I'm going to show you something that it always makes me kind of get all goosebumpy. Okay, this is some footage that was taken a long time ago by some amateurs who happened to be on the scene at the time that this was happening. We did the calculations and saw indeed that we could confirm that what was happening was in fact what was postulated. All right, let's take a look now. This is the Tacoma Narrows Bridge up there by where I was brought up in the town of Bremerton. And it is really, really in trouble. What's happening is that here's the bridge about 10 feet high or something like that, air going past it. The vortices that were formed behind it, like what I was showing in the picture, had a frequency that just matched the resonance frequency of the structure of the bridge, and threw it into these tremendous oscillations, which, as you can see, had a noticeable effect. Yeah. Now, can we calculate this? This is now one of the very first early calculations of this particular vortex street. We see streamlines and what are called streak lines that are moving there. It takes a little while, but soon the thing becomes unstable, starts wiggling a little bit more, and the force on this structure over here is now upwards and downwards and upwards and downwards, throwing the thing slowly into higher and higher amplitudes of vibration. Well, we did also tornadoes. Okay, we're going to go on to the next movie now. Okay, we did also tornadoes. The pictures of tornadoes that we have here are not terribly good, but they give you a feeling for the kinds of things that we wanted to calculate. They're old films that were the kinds that we were looking at back in those days. Very destructive. Some tornadoes are extremely destructive. And the question was, why? The National Science Foundation gave us a grant to examine what was happening in some of the most vicious of the big tornadoes. And there, you see, we've superimposed, this was a calculation now of the behavior of the tornado. And what we found is that centrifugal acceleration was throwing the air out when the tornado was intense enough. And in the middle, the air is moving down. Now, you can't see that the air is moving down until I get rid of the outer particles. The air is being sucked down from the clouds above. And that calculation was a very nice one to show the kind of behavior of this extremely intense kind of tornado. That has been an extremely useful sort of thing for us to calculate. And we use it all the time. What we have found is that when we do these calculations now with the most modern and sophisticated of the computational techniques, we get something which is very similar to what we got in the old days, but with much more sophisticated and generalized methodology, much finer resolution. And the contours in this are not contours of speed. And if you look at the velocity vectors here, you see they're up, down, up, down, up, down. And just like over here too, they are making for shear effects pushing upwards, pushing downwards, up and down, the way they were at the Kármán vortex street for the Tacoma-Narrows Bridge. Splash of liquid drop is a fascinating thing that has been a real unknown since the days that Edgerton took these fabulous pictures, unknown how to represent it, because the drop comes down, splashes out, and what we see is a bunch of little discrete things there. So this is now, what I'm showing you, is an effect of something that changes the turbulence. This is the effect of surface tension. And we show this fairly slowly, one frame at a time here. See how we're forming those droplets out on the side? That's an instability that you would say is closely related to turbulence, goes flying out in this corona, which very, very much like the things that were seen in some of the very high-speed photographs of a long time ago. Turbulence modeling. I've mentioned turbulence modeling, and I can't resist the temptation to at least show you one little part of it where we didn't calculate the details at all. Here again, we're trying to calculate what happens in a mixing layer, like what we saw earlier at the Texas A&M water tank, but we're trying to calculate the average across the layer of what's going on, so we get the layer thickness and the variations in density across the thing. Well, it was sort of frustrating. For years, we've been calculating these mixing layers pretty well. This is the high density side, and this is density as a function of position. But we always got this terrible bump in the middle. And that terrible bump didn't agree with the experiments, which are the dashed line. Well, what we found after some real careful thought is a technique how to really improve the modeling. A lot of times you learn by seeing where the trouble is. And we found what the trouble was. And now, when we look at the results, comparison with the stuff in England, okay, and the experiments at Chelyabinsk 70 in Russia, that the calculations, which are the solid line, just practically right on top of one another. And this, plus some other things, was enough to make a wonderful PhD dissertation. Well, let's take a look at let's finish up by taking a look at a few recent direct numerical simulation calculations that, I can say this because I didn't produce them, they just knocked my head off. They are so pretty. They use huge supercomputers, sophisticated numerical techniques, very fine resolution, and they're extremely useful. I hope I've indicated this, but expensive. We'll look first of all at the turbulence that occurs in the ocean. And this is going to be principally in the North Atlantic. You recognize where Spain is and North Africa and Florida and so on. And this shows now the sea surface temperature as a function of time. Of course, much, much faster than it really occurs in nature. But notice all those turbulent eddies that are sloshing through. I just get so carried away. I think, ooh, wow. They're really, really pretty exciting to see what's happening. Sea surface temperature again. Pretty soon we see the salinity down below the surface in the vicinity of the exit from the Mediterranean Sea. Mediterranean Sea is a lot more salty than the Atlantic Ocean because it evaporates and becomes salty. And so if you take the Straits of Gibraltar, the salty sea, heavy salty sea, comes out underneath while the relatively unsalty sea comes in the top. And here we're looking very deep at the behavior of those turbulent ocean currents. Another beautiful example that recently was performed, in fact, just within the last few weeks, is some calculations of a jet. What one has here, this is an experiment that they're proposing to do. What you have here is a magnesium plug in a plate of gold that's 800 microns thick, so it's, it's real tiny. And the thing is hit by lasers, heated very hot to the place where it then just expands, goes up into the top part, and makes this beautiful pattern. See the swirling, turbulent eddies that come out there? Oh man, I think that's really, really pretty beautiful. Now you can see why, I sometimes thought that I could have easily become an astrophysicist or a dentist. And I'm glad I went into what I went into because it has brought me into contact with so many exciting things. Well, our last example is a meteorite, or perhaps it should be called an asteroid impact. About 65 million years ago, there was a tremendous thing that happened in what is now the region of the Yucatan Peninsula. This great, powerful thing came crashing into the Earth, splashed up, and produced something that went around, and they now believe that it was that it killed off the dinosaurs. Well, Galen has done some beautiful calculations in which he has worked out what he thinks is probably the right mass and right velocity. And there it is. And see the crater that's formed there and the waves that are coming out and stuff coming. This is extremely hot material that comes out and floats around the whole world. And it's just, it's something really, really special to see. I thought we ought to see it 3 times because it is so pretty. Let me say that over these 50 years, it's been a really very special time. And I want to mention here several people. The ones who gave us these marvelous graphics. Nobody turned me down. We got these fabulous graphics, and Warren Young edited and assembled them in a marvelous fashion. And Jody Shepard and Will Parsons gave a lot of wonderful thoughts, guidance, helpful suggestion, and an enormous amount of hard work to bring all this presentation together. Now this sounds kind of nebulous, but to me, a very important part of the last years of all the years I've been here is the idea that I have made so many wonderful friends, associates, collaborators, people who furnish data, all kinds of things from every part of the laboratory. It's been a fabulous experience. To all the past and present staff of the theoretical division, starting from the early days of Carson Mark and others, many thanks. You gave us a fine home, have given us and are continuing to give us nurturing care, fine home, and we're real proud to be members of the T Division. But especially I'd like to thank all the past and present members of the fluid dynamics group. They've been like a family to me. I don't know how you feel about your own group, but to me, the group T3 has been like a family. I'd like every one of them to stand up for a moment so you can see some of them that are presently here. Come on, come on. And especially I want very much to thank my wife, Patricia, for her continuing love and encouragement and care and companionship. And I could go on, but she's a very special person. Stand up, Fatty. And to all of you who have come today, I want to say thank you very much.
Well, thank you, Frank, for a wonderful introduction to the world of turbulence. I think this is actually a tribute to your life creating what I would call the science of turbulence. And in that sense, Frank represents the very essence of Los Alamos to me in service to the nation, because he strongly believes, as I know, in the huge challenge of the national missions with which we are entrusted, but he uses that as a springboard, has used it, as you see, as a springboard to create new frontiers of science with an international impact. I had the good fortune about 18 months ago to visit with and interview Hans Bethe at Cornell. And he had many glorious Lionel stories to tell from previous decades, including ones about young Frank. And I'm not going to share all of them with you today, but I would like to say that Frank's passion and enthusiasm for his subject, which you just saw so elegantly, was the same that Bethe noted all of those years ago. Continues to this day, and each year that I've been at the laboratory, which is only 23 years, but each year I've observed new generations of Frank's students. Students can be undergraduates, graduates, they can be very mature physicists who suddenly discover a passion for turbulence. Interacting with Frank is a kind of fatal attraction and infection, because his knowledge, his insights, and his passion for the complexities of fluids, and as you really just saw, materials in a much broader sense, is so wonderful. As is his passion for our national security mission. So bringing those together is really special to see. I'd just like to say that Frank and Jody Shepard, who is sitting here, and talented members of the IM1 staff have been architects of a beautiful book, actually 2 books because it's in 2 halves, recording the 60 years of T division. This is now available, and it's a work, I think, of great care and attention to detail. And the point is that no one, at least no one in T division, but Frank, could have completed that. There is no substitute for having been there, so thank you, Frank. I'd just like to finish by saying, on behalf of your many admirers, many of them here, many of them who couldn't be here, we'd like you to know that it has been and is a privilege to have you as a colleague and a mentor, and to thank you for all these wonderful years. Thank you. That concludes the formal activities here, but let me remind you again, there's a reception starting immediately for Frank in the study center just across the way. Thanks again.